Hi, my name is Ishita. I'm a research scientist at the DeepMind New York City office. Thanks to the organizers for including me and inviting me. I'm sorry to not be there in person for what sounds like a really exciting lineup, but at least over video, I'm going to tell you a little bit about reasoning, our work on reasoning biases in language models. So to motivate this, I'll talk a little bit about this idea of abstract reasoning, and it's been the notion of abstract reasoning been central to our idea of intelligence, and therefore pretty central to our study of and development of artificial systems. And so to start off, what is abstract about this kind of abstract reasoning, right? And what is abstract is that reasoning in these situations is independent of content. That x is bigger than y logically implies that y is smaller than x regardless of what the variables x and y represent. So they're independent of the content of these variables. That's what makes it abstract. And a system that reasons abstractly is guaranteed to be systematic. It'll always reason the same way about a given structure. And logic is a classical example of systematic abstract reasoning. And deep learning's failure to be systematic in these ways is a common criticism that we've heard time and again. And so, as these new systems, these language models take the stage, there's been a lot of question about whether these language models are capable of what we would call abstract reasoning. And these models can perform above chance on several reasoning-like tasks, like math and logic, but they sometimes reason more accurately about frequently occurring situations. And according to several authors, this raises questions on the extent to which these models can fairly be said to be actually reasoning. In other words, language model reasoning doesn't seem to be abstract and that it does actually depend on content. So, on the flip side, what about human reasoning? The jury is still out on whether the best way to characterize human reasoning is with fully rationalist approaches versus more heuristic biased approaches. And there's been several decades of work on pursuing both of these ideas. And so it's definitely not a solved problem. And the key empirical effect that I'll focus on is specifically on content effects in logical reasoning. And this was exemplified very nicely by a famous study by Wason, where he showed participants these cards, as you see on the in the image, and asked them to falsify this rule that if even number, then red, and ask them specifically which cards they need to flip over to try and falsify this rule. So most people check the even number, which is the right thing to do, but then they also check the red card, which is the wrong thing to do. The right thing to do is to actually flip the brown card over to try and falsify if even number, then red. So many people get this wrong. But if you just embed this exact same logical structure in a familiar social situation, specifically, you change the numbers to be ages and you change the colors to be drinks, and you ask people if somebody's drinking an alcoholic drink, then they must be over 21 years of age. Then people immediately know which cards they need to flip over. And there are many approaches to try to understand this effect in humans, but a key reason that this difference comes about is that human logical reasoning doesn't exist in an abstract space. It exists within the context of our actual worlds, and we have beliefs over these worlds, over the entities over which we actually have to usually do abstract or logical reasoning in our everyday life. And what precipitated this work for us was that language models also have such real world so called beliefs, right? Language models have prior expectation over language. That's like their whole point. That's what they were trained to do. And and language often reflects human biases and knowledge. So you would expect these content effects or these belief bias type effects they might show up in language models as well. Specifically, if you think about the Wason example, like a language model already does know things about, for example, the fact that age is relevant to which and when you can drink, etc. So this is information the language model already has. And so the question we wanted to ask is, will the content information interact with logical reasoning in language models the same way that they do in humans? In other words, will language models show the same content effects on reasoning as humans do? So to evaluate this, we built a bunch of new data sets for evaluating these kinds of content effects. Specifically, we made these from scratch rather than using previous existing stimuli from psychology experiments because of the worry that there might be training data set contamination issues. So these data sets were generated such that we generated them for a few different logical tasks. The one I'll walk through here is the NLI task, or the natural language inference task, where people are given sentences like, if C's are bigger than puddles and puddles are smaller than C's. So you'll see that in this particular example, this is a consistent example where this phrase is not only logically correct, but it's also factually true. Then you have the violate condition of, if puddles are bigger than C's, then C's are smaller than puddles. This is a logically valid inference, but the sentences are false. They violate previous beliefs. And you also have a nonsense condition of, if WUFs are bigger than FEPs, then FEPs are smaller than WUFs. And so you can embed this sort of abstract structure where you have a consistent, a violate, and a nonsense condition by changing the actual x's and y's, the variables over which the logic operates, but the logical structure stays consistent and is always logically consistent in all cases. So we also embed these into syllogistic reasoning. I won't go over that in detail. It's all in the paper, of course, as well as in a Wason card selection type task. So what happens when we try to actually examine what the language model does in these situations? So in this situation, the language model is given the text that's in black and then is asked to make a forced choice between this, is asked to produce this blue text, and it has a few different options among which it has to choose. And we see that both in a smaller 7 billion sized model and an 80 billion sized model, Chinchilla, which is one of DeepMind's models, we see that it is significantly that belief consistent inferences are endorsed much more often. Natural language inference was our simplest task, so we tried a few ways to improve its performance because it's a relatively simple task and a language model should be able to do this. We just changing the instructions in the prompt actually makes a big difference. If you just say, instead of just giving it this task, giving it this problem, you explicitly say, solve the following logical task, and the performance on the right, as you can see, when it does, the gap is significantly reduced. And similarly, just seeing a set of nonsense examples in the context also significantly improves its performance. So this is just sort of showing that it's not an irreconcilable issue, that similar to studies in humans where various kinds of instructions can improve people's logical reasoning, so, instructions and examples can also improve logical reasoning in language models in these cases. And for the syllogistic reasoning, we also saw a similar pattern. I've just given an example here on the slide. Like humans, we find that Chinchilla is biased by the believability of the conclusion rather than by the logical validity of the whole argument. And in the Wason card selection task as well, we see again a similar effect where basically in most of the conditions, it's a pretty hard task. Even humans do pretty poorly, and the language model doesn't do super well either. But the one case in which it gets pretty good performance, where the dotted line here is chance, is when all of the entities over which it's reasoning are realistic and gets more than 50% accuracy in those cases. So in the study, we basically found that across three different tasks with de novo stimuli, well, de novo to the extent that you don't believe that absolutely every combination of words has somewhere been seen on the internet, our language models reasoned better over realistic, in other words, not abstract or nonsense entities. And so now this raises the question of what can we actually even learn from these results, right? So there are two main hypotheses that we can investigate. One is that language models are learning to imitate human-like biases from their human-generated training data. So this is just the reasons they show these biases is because these biases are in the data and they're just imitating those biases. And there are a few follow-up questions that would have to be true for us to believe this hypothesis, and these are testable predictions. Like, are these biases actually in the internet data? Are these biases abstract enough that they can be learned? This abstract bias can be learned and then applied to new stimuli. And the other hypothesis is that there's some convergent mechanism that gives rise to both of these effects, in both systems. And to answer that, to verify or consider that hypothesis, there are again follow-up questions like, are these biases normative under some circumstances common to both humans and language models? Can we uncover shared mechanism at some circuit or neural level to show that these are similar mechanisms? Is there anything we can learn about a convergent mechanism across both these systems? And these are sort of exciting questions we're interested in pursuing in future work. And with that, I'll just end by thanking my collaborators and giving you a citation to the paper I